Hello, everybody, and welcome to another great day of chemistry. So today we're going to be continuing from where we were previously at, which was looking at the ideal gases. So we're developing our equations of state and looking at how useful a ideal gas law can be to describe systems. But as I warned, not all of our systems are going to behave like an ideal gas. Some of them are going to have to break equations. And what we're going to be really doing here is looking at how do I evaluate systems that don't obey my simple equations of state? So, when we derived our ideal gas law, we made three key assumptions. So, the first was that our gases behave in a Newtonian fashion. So, they follow Newtonian mechanics in a relatively simple fashion. And this is actually going to be a fairly good approximation. The second one, however, gets a little bit more problematic. We assumed that the volume of the gas was much smaller than the volume of the container. So for a dilute system, this works pretty well. But we'll eventually get to this cases where the molar volume of the container is relatively small, and I have to start accounting for the volume of the gas. And then the third option was that all of our molecules underwent elastic collisions. So when two molecules came together, they were purely repulsive. Well, it turns out that also isn't true, and there's going to be some very specific circumstances in which molecules can start to be attractive. And so we're really going to be looking at these assumptions 2 and 3 throughout the next couple lectures. However, knowing that we made these assumptions isn't sufficient. We have to have a way to evaluate how accurate these assumptions are. And this being physical chemistry, we're going to go with our favorite option here. We're going to try and put a number to it. So we're going to try and place a numerical value to describe how accurate the ideal gas law is under a certain set of circumstances. And one of the most common methods is to use something called the compressibility factor. So this is going to be given a notation of Z. This is going to sometimes be uppercase and sometimes lowercase. So don't worry too much if you see it in this case, in either case, because Z is a factor we're going to use a little bit less than others. So we don't have to worry about it quite so much as like V. Speaking of which, the compressibility factor is simply given as the ratio of the real molar volume, so this is the one measured experimentally, versus the ideal molar volume. So that's what this not in the superscript is designating. And this is going to be the molar volume predicted by the ideal gas law. So we can imagine inputting the ideal gas law for a more complete version. So this ideal molar volume is going to be controlled by the measured temperature and pressure. And so what we're really looking at with the compressibility factor being the ratio of these molar volumes is, to a certain extent, the Z will be telling me about what is the relative error in the ideal gas law. And what we can do is, by again inserting this ideal gas law, we can formulate it a couple ways. So we can insert the ideal gas law, the molar, the Z equation into the molar, into the ideal gas law, where this is the ideal molar volume, to get our equation. And when either way that we get this, we can imagine rearranging the equation to show we can rewrite the ideal gas law to account for how much it fails. So we insert the compressibility factor into our ideal gas law. And again, note that we're writing this in terms of molar volume and not just volume and moles. So when we do this, one of the things that we're going to note is that this compressibility factor is more or less going to act as a fudge factor. It's going to account for everything that we don't know about the ideal gas law. So if the ideal gas law works very well, Z is going to be 1. If it doesn't work quite so well, it's going to start to becoming a different value. Now, the problem is we need to evaluate what is the physical meaning of Z so that we can predict when the ideal gas law will work and when it will not. So to do this, we first need to look at the physical meaning. So as I said, there's going to be three major cases we can examine for the compressibility factor. The easiest one is Z is going to be equal to 1. In this case, we just get the ideal gas law back. The system behaves ideally. But what happens if that Z is greater than 1? So what's the physical meaning of that? So if the Z is greater than 1, looking at our uh, modified gas law, we'll note that that means that we're going to have a much higher pressure than expected from the ideal gas law. That means that this container is going to exert a lot more pressure. The gas is going to exert more pressure on its container than we would otherwise expect from the ideal system. Now, that means that if I'm going to try and push on this gas or compress it, it's going to be much harder to compress than for an ideal gas, meaning it's going to be a lot more repulsive. And this is actually the origin of why Z is called the compressibility factor, is because it's going to tell me about how easy it is to compress a gas. Conversely, we can always also imagine if I fix the pressure, if Z gets larger, then that means the molar volume has to also be larger to compensate. That means that if I have a high compressibility factor, the system is going to want to expand. It is very poorly compressible uh, into a larger system. Now, the reason for this is actually because what we've done is we've underestimated the repulsion of the gas molecules. So if the Z is large, this means that the gas molecules have a lot more steric repulsion. They're pushing on each other much more than expected in an ideal system. Now, we'll examine later why this might be the case. Now, let's look at the other case. So if Z is very small, we have a very low compressibility factor. That means that the pressure would be much smaller than would be predicted for an ideal gas. So that means that this gas is going to exert less pressure on its surroundings, meaning that it will be much easier to compress because you don't have to fight against so much external pressure. So again, a high Z means it's very hard to compress. A low Z means it's very easy to compress. And we can also look at this from the volume perspective. If Z is small, then the molar volume will be smaller than expected. That means that if I have a gas with a low Z, that means that it will naturally compress itself more and occupy a smaller volume. Now, if we're looking at the molecular origin, if a high Z is due to extra repulsive intermolecular forces, this means that a low Z means that we have extra attractive intermolecular forces. So something is causing these gases to attract each other much more than we would expect. Now, the issue here is that the Z won't be fixed for a given gas. The Z can actually depend on a lot of external factors. So first one we can look at is the pressure dependence. So as I change the pressure of a gas, we'll actually see the compressibility factor change as well. And so what you'll notice is that as we increase the pressures, we tend to generally see an increasing Z factor because as the gas gets more and more compressed, it will start to show more and more repulsive forces. But notice that this is often might not be the case until you're above 400 to 600 ATM. So this is really high pressures. At these medium pressures, however, we see something a lot more interesting. Because under these low to medium pressures, again, this is going to be usually somewhere in about 1 ATM to 400 ATM. Again, depending on the identity of the gas, we actually see the Z start showing an attractive property as the intermolecular forces are going to be a lot more attractive, leading to a lower compressibility factor, a Z below 1. So again, we note some very interesting features depending on the identity of the gas. Now, the other thing we have to look at is temperature. Now, one of the things that is worth noting is if we get the pressure high enough, no matter what, the gas will become so closely packed that the gas molecules can't help but push on each other, no matter the identity of the gas, no matter the temperature. If you go far enough pressures, this is always going to be the case. But at these lower temperatures, we have this much more interesting phenomena because as the temperature is relatively high, what happens is these gas molecules are going to keep bouncing off each other, and these repulsive forces dominate, and the Z will always be positive. So if you get a high enough temperature, everybody's repulsive. However, if you get to a very low temperature, well, at this point, the gases can start to attract each other and the Z can drop below 1. Now, if at low temperatures gases are repulsive and low temperatures gases are attractive, high temperatures gases are repulsive, that means there's going to be some middle temperature at which the gases are something in between. So this temperature is called Boyle's temp. So at this point, the attractive features and the repulsive features cancel out, and the gas will behave ideally at least up until some given cutoff of a low pressure. Again, the exact cutoff of that pressure will depend on the identity of the gas. So now we've got an idea that we've got this weird mix of attraction and repulsion, and it depends upon three key things: the identity of the gas, the pressure, and the temperature. Now, one of the ways we can really examine when each of these cases will dominate is to actually look at how gases interact. So for any arbitrary pair of gases, for a given internuclear separation, there's going to be some middle distance at which the gases are going to have a potential well, where the gases will be more attracted to each other, pulling them together. However, if you get far enough out, this will essentially level off and gases won't see each other. If you press gases too far together, you run into this repulsion region where they're going to try and push each other away. Now, this becomes really important because the ideal gas law assumes that all gases are fairly far separated. That means they're in this region where they really don't see each other. That means that if we increase that pressure just a bit, so we get to these more middle pressures or relatively low molar volumes, what we've done is we've forced these gas molecules to get close enough that they're into this middle distance and they start to attract each other, pulling them together. So if, for example, if I put if the density says the gases will mostly be at this distance, they will now officially end up pulling the well, and you'll see some clumps and some separations because they've attracted each other just enough. However, if I increase the pressure too much, now I'm trying to force the gases much closer than they want, and we're entirely in the repulsion region. So moderate pressures, gases will see each other and say, hey there. High pressures, and it's like putting a bunch of people in a stadium and everybody wants their own personal space and they'll push away from each other. Now, this is also where temperature comes into play. Because let's say I'm in this middle region where I should be relatively attractive. If I'm in low temperature, everybody's moving slow. I'm going to saunter away to my nearest partner and I'll see them and we'll hang out together. But at high temperatures, this means high kinetic energy. You're bouncing around too fast. So if I go ahead and get put right here, I'm just going to run around, hit the repulsion wall, and just go in the opposite direction. So if you have low temperatures, you can go ahead and settle into a good state. High temperatures, you're just moving too fast to ever see this attractive region. So that's the play of these three roles. Gases with strong intermolecular forces will be more likely to attract neighbor. But if the pressure is too great or the temperature is too great, well, it's not going to count for a lot. So let's go ahead and try and see how some of these things play out. So we're going to do this by looking at CO2. CO2 is a fairly nice gas that's relatively well behaved. And at temperatures that are relatively high, so 50 degrees or higher, we'd expect the gas to obey the ideal gas law, where I'm seeing this nice inverse relationship in between the pressure of the gas and its molar volume. So as the molar volume decreases, the pressure has to go up because I'm putting the gas together, so it's going to push on the surroundings. But it's in a very inverse direction. Again, notice the axes here aren't perfectly proportional. However, something very interesting happens when I get to a lower temperature. So once the temperature gets just a little bit lower, what we start to see is under these low molar volumes, we start to see this attractive property start to kick in. And instead of a simple, nice inverse relationship, we start to see this relationship. And again, since we're looking at a constant temperature, this is our isotherm, that this isotherm starts to kind of not have as much repulsive properties I'd expect. And this is because we're starting to see that Z become a little lower and pull the gas together. And then as we decrease temperatures further, this gets amped up until we reach a very important point. And this is the point where the isotherm actually flattens out. So it's not that it's not as repulsive as it should be, but at this point, if I compress the system, it doesn't increase the pressure for a split moment. That point at which it happens is called the critical point. And the temperature at which this first happens is called the critical temperature. So for CO2, the critical temperature is about 31 degrees Celsius. Now, the reason why this critical point is very interesting is because it's sitting there overlapping three key phases. So in this beige region, what we see is this is the region where we indicate that CO2 now will form a liquid. Congratulations, you can't use an ideal gas law to describe a system that's an actual liquid. However, to the left of this critical point, we form a region where CO2 forms a supercritical fluid. So this is something that essentially moves like a gas, but has the density of a liquid. So it's kind of its own phase. We won't talk about it too much, but we'll play around with it a little bit in some later chapters where we're really looking at changes in phases and not simple equations of state. So that's where this critical point becomes really interesting, is now we're no longer just dealing with gases. This designates when I'm crossing over into other systems. And the nice point is every gas has its own unique critical point that defines a given temperature, the critical temperature, a volume, the critical volume, and a pressure, the critical pressure. So again, very distinctive point that's unique for every given gas. Now, the moment your temperature goes below that critical temperature, then we have some fun bits. Because at large molar volumes, the gas will still go ahead and obey the ideal gas law. But as you cool down, or as you compress the gas, the Z now starts to become more attractive until you get to a critical point. And at this part, as I compress my gas, the pressure doesn't change. And the reason why is because the gas is condensing. So the amount of gas in the atmosphere doesn't change because while I'm compressing the system, that extra gas is just condensing out into liquid until I compress it to such a point that I've now made a critical fluid. And so again, it starts to obey its own rules. And this will occur for every temperature above the critical point if you compress it enough. For high molar volumes, not a worry. And again, note in these cases, we're looking at molar volumes entirely below 1. And as a reminder, the molar volume uh, for atmospheric gas is closer to 22. So it is worth noting that these are high compression systems. But it also shows a very important point of when will I expect the gas to behave the least ideally? It's when it's not a gas at all. And this is one of the reasons why we tend to see gases fail at low temperatures and high pressures, because that's how you make a gas, a liquid. So that brings us to our description of how we can use the compressibility factor to evaluate the ideality of a gas. Next two lectures, we're going to be looking at how I can examine and mathematically treat a non-ideal system. So next up, we're going to look at the virial equation. Until then, take care.